Good morning. Welcome to our Red Short webinar for this Wednesday, April 26th. My name is Felicia Schenkelberg, and I'm an analyst with Red Sky Alliance. Today, I will be walking you through a short discussion of some released information on a break in the RSA crypto system. As always, you can find information on related topics at redskyalliance.org. So the agenda for today, we will begin by covering cryptography and how it plays a significant role in ensuring the confidentiality, integrity, and authenticity of data transmission. Next, I will move on to discuss one of the most widely used cryptographic systems, which is the public key crypto system of RSA. After that, I will discuss recent research suggesting that the combination of classical and quantum computing could enable the cracking of RSA. And then lastly, I will note how this information highlights the need for a transition to post-quantum cryptography over insecure networks, such as the internet. Let's get started. All right, so cryptography in general refers to the practice of creating and using codes and ciphers to secure communication and information. The encryption algorithm is a cryptographic algorithm that takes as input a plain text and an encryption key and outputs a ciphertext. The decryption algorithm is a cryptographic algorithm that takes an input the ciphertext and a decryption key and outputs a plain text. The encryption key is a value known to the sender, while the decryption key is a value known to the receiver. The decryption key is related to the encryption key, but is not always identical to it. In a public key crypto system, the encryption key and the decryption key are fundamentally different. For this reason, public key crypto systems are sometimes referred to as asymmetric crypto systems. And in such crypto systems, it has been considered computationally infeasible to determine the decryption key from the encryption key. And this is because public key crypto systems like RSA involve exponentiation. However, if the interceptor knows the algorithm used, in the case of secure communication over the internet, where RSA is the most common, the interceptor can attempt to determine the plain text by cracking the RSA encryption algorithm. So for RSA encryption and decryption, the encryption formula is the ciphertext, where it's equal or set to be equal to the message raised to a public key exponent, so that's E there. And this public key exponent is typically 65,537, and this is what's the default and what's typically used, and then it's modulus n, and where n is the product of two large prime numbers. And then for decryption, that message is sent or set equal to the ciphertext raised to D there. So that's going to be the private key exponent, and then that's going to be modulus n. So what does this mean? So the RSA encryption formula involves computing the ciphertext by raising the plaintext to the public key exponent modulo, and it's a product of two large numbers. So this decryption formula involves computing the plaintext by raising the ciphertext to a private key exponent module, the same product of prime numbers. So to determine the length of a private key in RSA, you have to consider the specifics of the public key crypto system. And in RSA specifically, the decryption key, D, is a number module n. This means that the decryption key can be any number less than n. So the maximum number of bits that we would need to represent an RSA private key is the smallest number k, such that 2 raised to k is less than or equal to n. Public key crypto systems tend to be referred to directly in terms of their maximum private key lengths. So when someone refers to a 3072-bit RSA, they mean the modulus n is 3072 bits long when written in binary. And as a result, the maximum private key length is also 3072 bits. So the process of cracking RSA encryption, the RSA encryption algorithm, involves the exhaustive key search for private keys. So for RSA, an informed exhaustive search would consist of trying private keys having the necessary mathematical properties. So like, for example, not all 3072-bit numbers are possible values of D for RSA. To perform such a search, we need a means of determining which keys are valid candidates for private keys. The catch is that finding this means that determining candidates tend to be related to solving the underlying hard problem. In the case of RSA, you need to know the factors of n to determine D. All right, so a recent study by Chinese scientists claimed that combining classical and quantum computing could enable the cracking of the RSA algorithm with a key length of 2048 bits, which is fundamental for the operation of internet protocols. While it's been widely accepted that a quantum computer had the theoretical ability to perform this ultra-fast factorization of larger prime numbers, such as the modulus necessary for RSA encryption, it was assumed that a quantum computer complex enough to crack RSA would not be built for several more decades. However, this research published at the end of 2022 displays breakthrough made by optimizing the Schnorr algorithm. Researchers were able to factor 48-bit keys on a 10-qubit quantum computer, and even claim that their algorithm can be scaled to use a 2048-bit keys using a quantum computer with only 372 qubits. It should also be pointed out that the quantum speedup of this algorithm is unclear due to the ambiguous convergence of the QAOA, and this is the convergence necessary to figure out what n is. So while increasing the size of the prime numbers in RSA can help make it more resistant to the quantum computers, this is not enough to make RSA completely secure against quantum attacks. So the existence of quantum computers capable of breaking RSA today highlights the need for a transition to post-quantum cryptography. So in summary, we discussed the use of cryptography for securing communication and information. We explained encryption and decryption algorithms and how they work in public key crypto systems like RSA. And then we also addressed recent research suggesting that the combination of quantum computing and classical computing could enable the cracking of RSA with a key length of 2048 bits, which is fundamental for the operation of internet protocols. This highlights need to transition to post-quantum cryptography as soon as this year, 2023. So with that, we have reached the end. Thank you for joining us. I hope you enjoyed the material and found it useful. If you have any further questions on the subject, you can contact us via Jim McKee at jimmckee@wupaclabs.com. I hope you have a nice day, and we hope to see you again next week.